Problem 5.2 on LMTD. A simple heat exchanger consisting of two concentric flow passages is used for heating 1110 kg per hour of oil having a specific heat 2.1 kilojoule per kg per Kelvin from a temperature of 27 degrees Celsius to 49 degrees Celsius. So in this case, concentric tube heat exchanger is there. It is also called as double pipe heat exchanger, where oil is being heated from 27 degrees Celsius to 49 degrees Celsius. So here oil is a cold fluid. The oil flows through the inner pipe made up of copper having outer dia 2.86 centimeter and inner dia 2.54 centimeter. And the surface heat transfer coefficient on the oil side is 635 watt per meter square. The oil is heated by hot water supplied at the rate of 390 kilojoule per hour and at an inlet temperature of 95 degrees Celsius. The water side heat transfer coefficient is 1270 watt per meter square Kelvin. So oil is a cold fluid and hot water is a hot fluid. It is also mentioned in this problem, in concentric tube heat exchanger, oil, that is cold fluid, is flowing through the inner tube and hot water is flowing through outer tube. So we have to represent oil flow through the inner tube, and any property of oil will be represented by suffix I, because oil is flowing through inner tube, and any property related to hot water, that is hot fluid, will be represented by suffix O, because it is flowing in the outside tube. Take the thermal conductivity of the copper to be 350 watt per meter Kelvin and the fouling factor on the oil side and water side to be 0.0001 and 0.004 meter square Kelvin per watt. What is the length of the heat exchanger if it is parallel flow and if it is counter flow? So let us summarize what are the informations given in the problem statement. Information number 1 is it is double pipe heat exchanger or concentric tube heat exchanger. Oil is a cold fluid, hot water is a hot fluid. And number 2 information, oil is flowing through the inner tube. So all the properties of the oil will be followed by suffix I, and hot water is flowing through outside tube. So all the properties of the hot water, hot fluid, will be represented by suffix O. And here fouling phenomena is taking place. So fouling factors will come into picture. Inner tube is having outer and inner dia, so it is having sufficient thickness and its material will have finite thermal conductivity. So let us mention here hot fluid is hot water, and cold fluid is oil. So let us first draw the schematic for this problem. In this case, concentric tube heat exchanger is, we have to find out the length of the concentric tube heat exchanger if parallel flow is employed, and length is to be found out if counter flow is employed in case of this heat exchanger. So figure 1 represent concentric tube heat exchanger with parallel flow. As mentioned in the problem, oil, that is cold fluid, is entering through inner tube, flowing through the inner tube, entering at the left hand side and leaving the right hand side. In case of parallel flow, hot water will also be entering into the left hand side and will be leaving on the right hand side. At temperature, figure 2, temperature variation of hot and cold fluids is shown considering parallel flow arrangement. Similarly, figure 3 represent concentric tube heat exchanger where counter flow is employed. Inlet of oil, that is cold fluid, is outlet of hot fluid, hot water, and outlet of cold fluid, oil, is inlet of hot fluid, that is hot water. And temperature variation for both the fluids is shown in figure 4. So temperature of the hot fluid is decreasing from THI to THO as fluid is moving from left to right. On the contrary, temperature of the cold fluid is increasing from right hand side to the left hand side, from TCI to TCO. In both the cases, mass flow rate of cold fluid is m dot c, which is constant, and mass flow rate of hot fluid is m dot h, which is also constant. Now, since outer dia and inner dia of this inner tube heat exchanger is given, so let me draw this surface of the inner tube on the larger scale or enlarged view. So if I could draw the enlarged view of this surface of inner tube, it will be represented somewhat like this. It will have inner dia represented by Di and outer dia represented by DO. The material of this inner tube will have finite thickness and will have finite thermal conductivity K. Since fouling factors are also given, that means fouling phenomena is taking place inside and outside of this inner tube. Now, as shown in this figure, the green color surfaces represents fouling on inner surface of the tube and outer surface of the tube. And effect of this fouling is to reduce heat transfer rate and will be taken into consideration by fouling factor for both the surfaces. That is fouling factor for fouling on inner side RFI and fouling factor for fouling on outer side, that is RFO. Now, after drawing the schematic, let us enlist all the given parameters. So let us enlist all the parameters on hot fluid, that is hot water side, and on cold fluid, that is oil side. So we have already gone through this problem statement. Different parameters are given like temperatures, heat transfer coefficient, fouling factors, mass flow rate, and OD and ID of inner tube. So parameters given on the hot fluid, that is hot water side, is mass flow rate of hot water m dot h 390 kg per hour. Let us convert this into kg per second. 325 by 3 kg per second. Specific heat of hot water Cph is equal to 4.2 kilojoule per kg per Kelvin. We will assume this because if one of the fluid is water, its specific heat is not generally given in the problem statement. So this is the most universal value and most generalized value. So we will remember it and we will assume it as 4.2 kilojoule per kg per Kelvin. Inlet temperature of hot fluid is given as 95 degrees Celsius. Outlet temperature is not given. So we have to calculate it from the relations available. Then hot fluid is flowing on the outside of the tube. So its overall heat transfer coefficient U suffix H will be represented by U suffix O, and it is given as 1270 watt per meter square Kelvin. Similarly, fouling factor on the hot water side or outside of the tube is 0.0004 meter square Kelvin per watt. The parameters given on the cold fluid, that is oil side, are mass flow rate of cold fluid m dot c 1110 kg per hour, and in kg per second it is 925 by 3 kg per second. A specific heat of oil CPC is equal to 2.1 kilojoule per kg per Kelvin. Inlet temperature of cold fluid oil is TCI 27 degrees Celsius. Outlet temperature TCO 49 degrees Celsius. Overall heat transfer coefficient of the cold fluid represented by UI will be 635 watt per meter square Kelvin, and fouling factor RFI is given as 0.0001 meter square Kelvin per watt. Outside diameter of the inner tube is given as 2.86 centimeter, 2.86 into 10 to power minus 2 meter. So outer radius RO will be 1.43 centimeter or 1.43 into 10 to power minus 2 meter. Similarly, inner diameter of the inner tube is given as 2.54 centimeter and radius is RI 1.27 centimeter. In meter it will be 1.27 into 10 to power minus 2 meter. And thermal conductivity of this material of the inner tube is given as K 350 watt per meter square Kelvin. So after drawing the required schematic representing all the parameters, after enlisting all the given values, let us make some assumptions. Now these are the same assumptions which are considered during the derivation of relations for LMTD for parallel and counterflow heat exchanger. So assumption number 1 is one dimensional steady state heat transfer. Assumption number 2, no change in kinetic energy and potential energy of both the fluids. Assumption number 3, no heat transfer due to conduction along the axial direction of the heat exchanger. Heat conduction takes place, or heat conduction is considered to be taken place in radial direction of the heat exchanger only. 4. Heat transfer due to radiation is negligible. 5. Outer surface of heat exchanger is perfectly insulated and hence there is no heat loss from the heat exchanger. And assumption number 6, value of overall heat transfer coefficient is constant. Point number 4, we have to enlist what are the parameters to be found out. So we are supposed to calculate length of the heat exchanger if parallel flow is employed, that is L suffix PF, and 2, length of the heat exchanger if counter flow is employed, that is L suffix CF. So in order to find out the length of the heat exchanger in different direction of flow, the calculation will proceed in this manner. Let us first recall the expressions for heat transfer rate from heat exchanger. And this expression is nothing but capital Q, and it is given by UO AO into LMTD is equal to UI AI LMTD. Now this expression for LMTD can be used depending upon whether it is parallel flow or counter flow heat exchanger. If I further simplify it, since I am supposed to calculate length of the heat exchanger, AO is nothing but area of the heat exchanger on outside radius basis. So it can be calculated as pi DOL into LMTD is equal to UI AI is surface area of the heat exchanger based upon inside diameter or radius into LMTD. Let us say this is equation number 2. So in order to find out the length of the heat exchanger, I must know the heat transfer rate, UO or UI, then length of the heat exchanger and LMTD expression. Now before moving further, one more important point worth remembering while dealing with the LMTD method for analysis of heat exchanger. LMTD method can be satisfactorily used only and only if all the 4 temperatures of hot and cold fluids are known to us. In our case, inlet and outlet of cold fluids are given. However, inlet temperature of hot fluid is only given. So I need to calculate outlet temperature of hot fluid as well, because LMTD expression will involve all the four temperatures THI, THO and TCI, TCO. So to calculate this THO, let me take this condition. We have assumed one dimensional steady state heat transfer. So under steady state heat condition, rate of heat transfer from heat exchanger is equal to rate of heat transfer given by hot fluid is equal to rate of heat transfer taken by cold fluid, or Q is equal to m dot H CPH into THI minus THO, and this will be equal to m dot C PC TCO minus TCI. Let's say this is equation number 3 and this is equation number 4. Now a close observation of equation number 3 and 4 will give me an idea that m dot H is known to us, m dot H CPH, m dot C CPC, TCO and TCI are known to us. So if I take these two equilibrium equations, we can easily calculate TCO, THP. So let us take from equation 3 and 4. At this moment I will neglect the Q. So from equation 3 and 4, now let us put all the values. M dot H is 325 by 3, CPH is 4.2 and THI is 95. (925) by 3 into 4.2 is CPH and THI is 95. THO is to be calculated. Similarly, m dot C is 325 by 3, CPC is 2.1, TCO is 49 and TCI is 27. So solving this energy balance equation will give me the value of THO. So this way we will be in position to find out fourth temperature. So this comes out 63.69 degrees Celsius. Outlet temperature of hot fluid is this. Now all the four temperatures are known to me. So using either equation 3 or equation 4, I can calculate the rate of heat transfer, because in equation 1 or equation 2, I maybe require the value of Q to calculate the value of L. So let us calculate from either equation number 3 or 4. So I am taking equation number 3. From equation 3, that is Q is equal to m dot H CPH THI minus THO. M dot H in kg per second is 325 by 3. CPH, that is specific heat of hot water, is 4.2. THI is 95 degrees Celsius and THO is 63.69 degrees Celsius. So from here the value of Q comes out here in this equation. There is a calculation mistake. Let me correct this. The mass flow rate of the hot fluid is let me correct this one. The mass flow rate of hot fluid is this. So mass flow rate of hot fluid is 325 by 3 into 4.2 into 95 minus THO, and mass flow rate of cold fluid is 925 divided by 3. So this THO will have a changed value. Okay, so still this value comes out 63.69 degrees Celsius THO. So considering this, the temperature THO 63.69 degrees Celsius, the rate of heat transfer will come as so the value of heat transfer rate comes out 14,246.05 kilojoule per second or kilowatt. So this will be the value of rate of heat transfer. Now after calculating THO and heat transfer rate Q, I need to calculate the length of heat exchanger when it is parallel flow and length of heat exchanger when it is counter flow. So equation 3 can be used in two situations. One is parallel flow heat exchanger, another is counter flow heat exchanger. So let us do this one by one. So case 1 will be parallel flow heat exchanger. So equation 3 can be modified in this fashion. Now here one more thing it is worth explaining. You can take either of the equation, that is equation of Q based upon U naught pi do L into LMTD or UI pi di L LMTD. It hardly matters whether you consider this Q based upon UO or UI basis. In both the case, answer will be same. So I am considering this equation 3 based upon outside area, that is UO. UO into pi do. So length will be L suffix PF and LMTD will also be calculated based upon outside area. And LMTD will be on parallel flow basis. So Q is known to me, diameter DO is known to me, LMTD for parallel flow is to be calculated and U naught is to be calculated. So let me give this as a equation number 5. Now expression for DO can be obtained from the heat transfer data book. Now I have this data book, Heat and Mass Transfer Data Book, 6th edition. It is by C.P. Kothandaraman and S. Subramaniam from New Age International Publishers, and its edition is 2009. So in this data book, on page number 156, this one, the expressions for overall heat transfer coefficient based upon inside and outside area are given. Okay, 1 upon U naught into 1 upon HO plus RFO plus RO by K into log RO by RI plus RO by RI, RFI plus RO by RI 1 upon HI. So we can use this expression. So this is the formula we have obtained from heat transfer data book for overall heat transfer coefficient. 1 upon U naught is equal to 1 upon H naught plus RF naught plus RO by K log R naught by RI plus RO by RI, RFI plus RO by RI 1 upon HI. Now let us put all the values which are given to us. So in this way we will be able to calculate 1 upon UO, overall heat transfer coefficient based upon inside area. Here once again I would like to mention, it is not necessarily you must always take U naught. You can take UI as well. As I said earlier, answer is not going to change. So let us get all these values of HO, RFO, RO, RI, K from the given values. So the value of HO, let me correct this notation here. This is the value of heat transfer coefficient, convective heat transfer coefficient, not of overall heat transfer coefficient. So heat transfer coefficient for hot fluid, this will be this will be H naught. Similarly, this value will be HC and this value will be HI. So H naught is 1270, RFO is 0.0004, RO is 1.43, RI is 1.27 and RFI is 0.0001 meter square Kelvin per watt and HI is 635. So HO is 1 over 1270, RFO is, that is fouling factor on outside radius basis is 0.0004, RO is 1.43, K is 350 watt per meter Kelvin, log of RO is 1.43 centimeter, RI is 1.27 centimeter plus 1.43 divided by 1.27, and the value of RFI is 0.0001 plus 1.43 divided by 1.27, and the value of HI is 635. Let me check once again whether I have plugged all the values correctly. Okay, all the values are plugged by me correctly. So I am directly getting the value of U naught by solving it. It will be in watt per meter square Kelvin. So the value of U naught comes out 281.05. We will be using this value to find out length of heat exchanger in parallel flow and counter flow heat exchanger both. So now in equation number 5, we know the value of Q, value of U naught, D naught. So LMTD for parallel flow needs to be calculated. So LMTD for parallel flow, I am directly writing this formula. Is nothing but delta Ti minus delta To to the log of delta Ti to the delta To. Let us have clarity of what is delta Ti, delta To in case of parallel flow heat exchanger. This will be delta Ti, that is Thi minus Tci, and this will be delta To, Tho minus Tco. So delta Ti is temperature difference between hot and cold fluid at the inlet. Thi minus Tci minus Tho minus Tco divided by log of Thi minus Tci divided by Tho minus Tco. Let us plug all the values of temperatures. So Thi is 95, Tho is 63.69, and Tci is 27, Tco is 49. Thi is 95, Tci is 27 minus Tho is 63.69, Tco is 49 divided by log of 95 minus 27 divided by 63.69 minus 49. So this will give the value of LMTD for parallel flow heat exchanger as 34.78 degrees Celsius is the LMTD for parallel flow. Hence, from equation 5, I can calculate the length of parallel flow heat exchanger. So, value of Q is from equation 5, value of Q is 14246.05, value of U naught is 281.05, into pi into outer diameter is 2.86 into 10 to power minus 2. Length of parallel flow heat exchanger is to be calculated, and the value of LMTD for parallel flow heat exchanger is 34.78 degrees Celsius. So here length of parallel flow will come out as 18.16 meter, and this will be the answer. Similarly, for case number 2, for counter flow heat exchanger, from equation 3, Q is equal to U naught into pi D naught into L counter flow into LMTD for counter flow heat exchanger. Let us say this is equation number 6. So I have the value of Q, value of U naught, D naught. So LMTD for counter flow heat exchanger is to be calculated. So LMTD for counter flow heat exchanger Now general formula will remain same, that is delta Ti minus delta To divided by log of delta Ti over delta To. Now here the delta Ti and delta To for counterflow heat exchanger are to be considered. For that we have to refer the schematic. So in case of counterflow heat exchanger, delta Ti at the inlet is this, that is Thi minus Tco, and delta To at outlet is this, that is Tho minus Tci. This difference is taken in such a way it will always be positive. So delta Ti will be Thi minus Tco minus Tho minus Tci divided by log of Thi minus Tco divided by Tho minus Tci. Let us plug all these values. So LMTD for counterflow comes out, Tho is 95, Tco is 49, Tho is 63.69, Tci is 27. Divided by log of 95 minus 49 divided by 63.69 minus 27. So LMTD for counterflow comes out LMTD for counterflow comes out 41.17 degree Celsius. Hence from equation 6, the value of heat transfer rate equation is this. So value of heat transfer rate is 14,246.05. Value of U naught is 281.05. Into pi into D naught is 2.86 into 10 to power minus 2 into L of counter flow into LMTD counter flow is 41.17 degrees Celsius. So solving this equation will give me the length of heat exchanger in counter flow heat exchanger as so LCF comes out 15.34 meter. So the length of heat exchanger employing counter flow is 15.34 meter and length of heat exchanger employing parallel flow is 18.16 meter. That means everything remains same just by employing the counter flow arrangement of flow. The size, the length and hence area and hence size of the heat exchanger can be reduced. So I can draw conclusion in counter flow arrangement size of heat exchanger will get reduced. So this way we can solve this numerical.